Hey, what's going on, y'all? Jay from JS Films. Now, one of y'all wanted me to check this out from my live stream. It's the real-time path tracing in Unreal Engine 5, presented by NVIDIA's Richard Cowgill. Super cool dude. Now, I was able to see some of this kind of like prior, kind of like work in progress, and it honestly blew my mind. So I'm kind of glad that they're sharing this now on the Unreal Engine 5 YouTube channel. So let's check it out.
Hey everyone, thank you for being here. My name is Richard Cowgill. I'm the RTX Unreal Evangelist at NVIDIA. Today we're going to talk about real-time path tracing in Unreal Engine 5. This is a pretty wild subject to be talking about real-time path tracing at this point. A lot of graphical advancements are happening very fast, and this is pretty exciting stuff. So
I want that shirt, dude.
Just to go over the agenda a little bit. We'll first talk about offline path tracing. And traditionally, path tracing is only offline. Like there's only one way to do it. So as we move into real-time path tracing, I'll talk about some of those differences and what that means, how it's different than offline path tracing, and what you gain by using it. There are new features that come along with real-time path tracing, some pretty incredible stuff. Some of it's kind of emergent, but some of it's very deliberate. And then I'll talk about the branch where you can get it. It's called the NVRTX branch. It's a free code branch online on GitHub that contains all of our ray tracing and path tracing code improvements, as well as a bunch of other stuff. So here's an offline path tracing example. This is being done in Unreal Engine. If you look at the bottom here, you'll see a thermometer bar slowly ticking away. Offline path tracing is very slow. It's expensive but accurate. It's expensive because it's sampling every single pixel, often recursively. So it'll sample a pixel, 500 times, 1,000 times, several thousand times sometimes. And there can be multiple bounces occurring along with that. So rays are being fired into the scene, and even a relatively simple scene like this, that's just basically a room, can take minutes per frame, hours per frame, and traditionally, going way back, this was days per frame.
Yeah.
So why is path tracing like this? Why is it so slow? It's seeking physical accuracy. It's firing rays into the scene in order to reproduce reality, essentially. That accuracy comes at a very high cost. This is sometimes referred to as ground truth, but the point is that it produces very pretty images when it's done, but it's expensive. So here's the same scene, same content in Unreal 5 using real-time path tracing. This is a technology that targets 60 FPS. So as a baseline, we want to make sure that you can hit a 60 FPS target, preferably higher, but if we're talking about games, you want to be at least 60. Sampling is sparse. If we're going to be real-time, we can't sample every pixel hundreds of times. We can fire millions of rays, but not billions. So we have to be smart and careful about the amount of rays we're firing into the scene. And it's important to note, real-time path tracing today doesn't path trace everything. Very specifically, we're path tracing direct lighting, indirect lighting, and some reflections, rougher reflections, specular information, that sort of thing. Mirror reflections are a different story. We still rely on ray tracing or lumen for that, but we make it easy to make all that work together, and I'll get more into that as we go along. Okay, so how does this work? Real-time path tracing, the core technology behind it is something called Reister. Reister, you can see at the top there, it's quite a mouthful. reservoir spatiotemporal importance resampling. We can break this down a little bit, but just so you know, over here, there's a QR code for a research paper on Reister that was published on the NVIDIA website 3 years ago. So if you want more detailed information, more background information on how it works, check that out. It's a very detailed read. But yeah, breaking this down a little bit, Reister technology works by doing several things. Spatial information is part of it. So it'll consider, as I said, it'll sample things in a sparse way, but an intelligent way. So in this example, where we have an arbitrary grid of 25 pixels, and we're sampling the center one, and from that sample, we're able to discern very useful information about neighboring pixels. Now, we're not just sampling this randomly. There is an intelligence behind it. We're getting hopefully a good sample, and that gives us a lot of information about how other pixels ought to look. Then we also consider information temporally, and that is to say previous frames. And the cool thing here is sometimes you don't need a lot of previous frames to get good information. You might just need to go back 2 or 3, sometimes 4 to 8. But the temporal information contributes to giving us samples in other locations. All of this information is stored in what we call a reservoir. So that's the first 3 words of the acronym. So this reservoir, you can think of as a screen space lighting information that's gathered and processed in a single pass and applied back to the scene. So this is one of the very cool features that comes about from Reister as a technology. It doesn't matter how many lights you have in the scene. They all count basically equally according to the algorithm. So we're no longer processing lights individually or denoising them individually. You can put 10 lights, 100 lights, 1,000 lights, whatever, into the scene and get roughly the same performance. There are additional steps like denoising. Denoising will take that reservoir data and take it a step further, cleaning it up, making sure that all the data is properly inferenced and cleaned up in a way where it's very high quality. So there's a lot of training that goes into this. We do have different denoisers that are available in the NVRTX branch. There's a couple of them, and they each have pros and cons. But it gives you different ways to get to the result you want. And so for this point, I didn't really have, I'll just say, I didn't really have another place to put this in the slide deck. I just wanted to note that real-time path tracing has kind of gone by different names at different points. Sometimes, like I said, the core technology is Reister. That's really that's the engine that makes it work.
You know what's funny about this? Because I actually talked to Rich about this. It's like the games that are coming out right now using this technology, they're all called differently. You know, some of them called sample lighting. So I was kind of telling him, like, wouldn't it be cool if we can just kind of like just use one term for it? So it gets kind of confusing for some people, especially with the different games. Like I know in Alan Wake 2, it's something else. You know, in Cyberpunk 2077, and it's something else. So it's RTX Di, okay, yeah, but it's Reister also in sample lighting, but it's the same exact thing. So this is good that he's going over this.
Sometimes it's referred to as RTX Di. In the NVRTX branch, for example, you will see options in the project settings, for example, to turn on RTX Di, in this case, RTX Dynamic Illumination, and that's how you enable real-time path tracing. RTX Di is not a technology by itself. It's more of an umbrella term for all of the real-time path tracing work that we're doing. And sometimes in code, you'll see it referenced as sampled lighting. So, yeah, again, I don't want to mix things up or make it too complicated. Just to say that sometimes you'll see it referred to by different names technically.
Nice, Rich.
Okay, so what exactly is real-time path tracing giving you? You gain out of it is physical accuracy. Your lighting will take a step up.
Yeah.
And you can see some examples of that here, where there's a lot of lights placed in the scene, some animated, some not. It doesn't really matter. You can just place tons of lights in the scene, and like I said, it doesn't really matter how many lights you have. Not only will they be path trace lights in terms of direct illumination and global illumination, but you'll be able to have lots of them.
So here's the actual scene that we created, kind of like a demo. I don't know if y'all have seen it. I'll put the link in the description below, but we did a live stream where Rich and I did like a little cyberpunk theme with RTX DI and stuff. It's amazing. Again, he talked a lot about the technology, and they're showcasing it here, which is sick.
Spotlights. How you place them doesn't matter either. So, you can imagine lots of different ways where you could really stress test the system. Put 100 lights just in one spot, see what happens. Any configuration of lights, like in any way you might use them, won't dramatically impact performance one way or the other.
If CD Projekt Red uses this in the new Cyberpunk 2077, yo, it's about to be crazy.
All this boils down to faster workflow.
Look at that.
If you don't have to bake your scenes anymore,
yay.
You don't have to set light attributes, cull them out, stream them out, or anything like that. You just flood your scene with as many lights as you want.
That's me.
And go after aesthetics rather than performance targets. We aim for compatibility and scalability with this technology. Compatibility in the sense that we're not doing anything in the NVRTX branch that requires RTX hardware specifically. It runs everywhere that ray tracing runs, which today is all hardware, all
That's
modern
awesome.
hardware. So you have broad platform compatibility and scalability in the sense that we build it in with Lumen. So you can use, for example, software ray trace Lumen at the low end, and then with some toggles for high-end hardware, you could enable path-traced GI and have that high-end look for like an RTX 4090.
5090?
Like I said, there are some new features that come about with all this. Translucent shadows, translucent colored shadows. I'll show you some examples of that. Emissive sampling. You can get direct lighting and global illumination from emissive surfaces. Every triangle becomes a light source. And particle effects. Niagara lights, Niagara lights can be shadow casting. So
yeah, it's so funny because in the demo that we made, he even made it so that the actual tracer coming from the weapons were shadow casting. Like every single tracer from the weapon was shadow casting. It was freaking bananas.
That's a significant improvement over hardware ray tracing today. If you like stats, I have some of that for you. So the top chart here shows frame rate on the side and light count at the bottom. And this is the orange line shows RTX DI or real-time path tracing, and how from everywhere from like 0 to 100 lights, there's basically very little difference. There's some fluctuation in performance, but not much. Whereas traditional ray tracing, especially if you look at the yellow line shows ray traced lights with some area to them, which is, how you'd want to use ray tracing or path tracing. You see that it falls off sharply as you add in more lights, and that's because they're being processed individually rather than all together. And in the bottom chart, so here we have same thing but extended out
more
to
lights,
1,000 lights.
Oh.
And you can see that it's not perfect.
It's starting to go down, a little bit, but that's still 1,000 lights.
Maintaining a very high frame rate, and I think some of this drop are things that we can learn and improve. But you can see that traditional ray tracing, some pass a certain number, 250 lights, it goes to nothing, and then, 400, 500 lights, it just stops working. So So the fixed performance overhead and the fixed GPU cost really helps you to construct scenes that just look good and focus on that. We include in the NVRTX branch engine scalability. So there are always CVARs to modify engine, and code that you can tweak. But out of the box, we try to give you very good options. So we piggyback on the Shadows engine scalability option, where you can go from, say, epic quality to high quality and maintain a really good look and really good performance and scale that across different hardware. Settings are also tweakable now in the post-process volume. In the past, we did this only through CVARs, and now we make it much easier for you to tweak it there. And the CVARs have been sort of reorganized and cleaned up.
So much better.
If you looked at this in the past,
it's so much better
you would
now.
see that it was basically a longer and sort of more labyrinthian set of console variables. But now everything is under r.sample lighting, and from there it's either direct or indirect, because you're always pretty much messing with your direct lighting, like your shadow casting lights, or your indirect, your GI and your what used to be ambient occlusion. Here's some pretty pictures, I hope. So on the left here we have Lumen by itself, and on the right is Reister enhanced with, or Lumen enhanced with Reister. And you can see a few things that this does. First off, I mean, just noticeably, the right image is brighter. And that
Bounces.
At least partially has to do with the fact that emissives are being properly counted in this scene.
Yep.
So for example, over here, you can see that these are just very thin emissive meshes. And Lumen, there's not enough resolution to, even with hardware ray trace Lumen, it can't see where this
Cyberpunk's gonna look good,
but
boys.
It's able to
It's bouncing everywhere
directly
yeah.
from the emissive, and sample that nearly per pixel. So you can get very fine resolution with that. But also you'll notice just generally shadows
softer, man.
will start to provide you a more fluid look, and you'll notice very precise grounding shadows. There's even a little bit of light right there that is missing in the pure Lumen image. And none of this is to say that Lumen is doing anything wrong or is bad or anything like that.
It's just enhancing it.
It's just that it's not sampling the scene in a completely per pixel way, whereas Reister is able to pick up a lot more details. And you'll notice the reflections look more complete and brighter as well. Like down here, there's some loss that's occurring, whereas the Reister image has got sort of more complete details. Yeah.
That's good sampled. Yeah, here it is. This is the demo. Awesome.
So here we have a test scene with about 300 shadow casting lights in it. There's
cool.
no special settings to any of the lights. This is just, like I was saying, one of the features that it gives you, where you can put in tons of lights. They're all technically path trace lights.
By the way, this is this character right here is one of my police officer for my Zinville cyberpunk world that I was trying to build. That's now dead.
Even in some cases, it's picking up lighting directly from emissives.
ZPD, baby.
But this particular scene wasn't tuned for that. It was just lots of placed lights. There was a little bit of that right here, actually, where there was an emissive added behind the fan, and then some shadows were created from that.
Such a cool scene. I love it. I wonder if he's going to show to a tracer.
You can see you get a lot of complicated shadow activity. There's a volumetric fog light there in the kitchen. And here's a little bit of editor usage.
Woo,
so here's all the lights being selected.
That's awesome.
It becomes a very free workflow way of doing your scene. So yeah, you can see just selecting one light source and moving it around, you get all the soft shadow attributes that you'd expect from it. This is a long point light, so it's been given a small radius and a length. And of course, it expands to all light types. So
he actually went ham on this. Like, the whole point of the demo was like overdoing it. So it was light crazy. It was light crazy because I was like, dude, it's cyberpunk. It's gotta.
Lights are kind of.
It's gotta be crazy
from a performance standpoint. When they were first introduced,
look at this.
They were definitely the most expensive light you could place in your scene, probably. Just the fact that they had this area associated with them meant that they probably had a little bit of additional cost.
This is really giving you Cyberpunk 2077 Part 2 like preview.
If you wanted every light to be a rec light and just have tons of them, you could do that.
Crazy, man. And I think YouTube is crushing the shadows a little bit, so it's a little bit dark, but trust me, the actual gameplay itself in editor and the package, it's good.
It gets a little bit excessive, right? Where here's 4 point lights, they're all fairly large radiuses.
Yeah, that's crazy, man.
They're all shadow casting and placed in the corner. That's not something you'd normally want to do. There's 2 rec lights above this.
This is like a cinematographer's dream.
Out. So it didn't matter if it was a masked material or a little bit of geometry there. It's able to cast shadows from it.
Crazy.
So here's an example of a path-traced forest. NVRTX has other features and optimizations in it beyond just path tracing. One of them is support for foliage meshes at scale that can be ray traced and path traced. This particular example scene even has a path traced skylight. Right now, skylights are only doing direct lighting, but in the future will also support global illumination from them. You'll notice all the foliage is animated and moving. That's because in the NVRTX branch we support world position offset animation. So that will work with path tracing, and you can see the effects of all that. This is an interesting demo. We call this the zero light demo. There's no actor lights in this scene at all. And this is one of the abilities that real-time path tracing starts to give you. You can light your scene entirely through physical materials. The glowing spheres there are just that. There's no actor light associated with them. And you can see that there's direct shadow, GI, reflections, all happening. And it's all from the real-time path tracer. This is an example of the pure path tracing mode. With real-time path tracing right now, we give you 2 options with it. You can either use it with Lumen and scale it in with Lumen, so it's like a good high-end option for high-end PCs, or you can use real-time path tracing by itself.
Crazy.
Which, it's not going to be like necessarily compatible with lower end hardware, but it allows you to do things like this. And this is just a view of the same cinematic, but from the editor point of view.
Wow. I actually use a lot of emissive lights in my Fortnite maps, and they're awesome. They're a lot cheaper. Really dope.
So here you can see the direct lighting that becomes possible. That's not a rec light that's being moved around. That's a little mesh.
Yeah.
Right. So you can drop a different material on it.
The specular on that.
And then you can control the number of bounces you get out of it and so forth.
And the reflections look accurate too from the light itself. Freaking nuts. Wow, emissive lighting, no lights.
This is I'd say lighting scenes this way is still a little bit experimental and a little bit new, and we're getting good initial results from it, but I think we've got a little bit more work to do to make it like really broadly useful. That's not to say you couldn't use it right now. I mean, this code is available right now.
That's awesome.
Cyberpunk,
man.
We're going to have some tweaks to it in the future that's going to make it even more robust. We're aiming to make this feature as good as actor lights, so you can literally every triangle in your scene can be a shadow casting light if you wanted.
Be a cool comparison, though. You have like a rec light or an emissive, just to kind of see the accuracy.
And there you can see in the foreground a little bit of what path trace reflections look like. Yeah, and here again is just it's almost sphere mesh.
It's almost as good as a point light, to be honest.
Very bright surface. And you can see some of the direct shadows you get from that and so forth.
I do like that fall off on that shadows too.
So yeah, here's a still frame chosen from the cinematic. On the left, we have the offline path traced. On the right, the real time. This was done. This was 60 FPS on a 4090. 6 samples per pixel.
6 samples.
We're aiming for 1 sample per pixel in all cases. So
insane, man.
This is to show that. Yeah, currently you can do this kind of lighting. You might have to up your samples a little bit. It might require maybe higher end hardware than you'd want at the moment, but long term we expect to improve that and make it more robust and better. But if you just compare the images, you can see that we're very, very close to the offline.
Skin there, man.
In fact, an interesting detail here is that the offline image is rendered, it's completely per pixel. So this is at 100% resolution, no upscaling. The real-time image is 50% DLSS. So we're getting, very good quality out of that. I'll point out, just so you guys you're really aware of it, where the real-time is falling short and where we want to improve.
Shadow right there in the reflection.
Down here at the specular highlight, you'll see that it's lacking some detail compared to the offline version. And if you look really closely at the direct shadow, it is very close to the offline version, but maybe lacking just a little bit of sharpness. Both of these differences largely it's not the real-time path tracer, it's not a fault of Reister, it's a fault of the denoiser. And so this is an area
it's
where
going too ham.
Make improvements, probably with no performance cost.
It's going too
better
ham.
Training of the denoising algorithm.
And that's one of the problems about I've covered the denoisers in Unreal, and that's one of the reasons why I don't use them when I'm doing cinematics. Is it just sometimes it goes too ham, and it makes it. I always kind of refer to it like a VIX. Kind of like if you take VIX and you like smear it on a lens, that's what it kind of looks like.
That'll happen over time. Here's another new feature. This is great.
Oh yeah, this was sick.
Real-time colored shadows, from translucent surfaces.
So if you have like balloons and stuff.
Stained glass windows. Here's just an animated material and, a path trace light casting through it. So you wouldn't have to fake that. Here's the other one I mentioned, shadow casting Niagara lights. So, with Niagara particle systems, you can go really crazy with light sources. Every single, emitter point can have
shadow
a
casting
light associated to it, and those can all be shadow casting. They generate path traced quality shadows. They can generate GI. They can generate volumetric fog shadows. So you gain all those abilities with this code. Okay, so things we aren't path tracing yet. We have some work to do. Like I said, we're not we path trace reflections, but not mirror reflections, very low roughness reflections. It's probably, well, there's a lot to talk about with that, but it probably started because real-time path tracing was more focused on direct and indirect lighting in its initial research, and and then it started to move into other areas. So right now, mirror reflections are ray traced or lumen, and you can set a blend point, right? So if you have a mirror in your scene, you can use lumen or ray tracing for that, and then blend it to path trace for the rougher surfaces.
Yep.
Translucency is still ray traced. I think this is probably I'll just say it's kind of my opinion. I think this is more of a performance issue than anything. I mean, ray trace translucency is expensive enough in the current hardware generation. Path trace translucency would be even more expensive, but there could definitely be improvements in both, in the algorithm and so on as we move forward on this. Hair and single layer water, they're still being ray traced. We don't lose compatibility with anything. I'll point that out. It's kind of an important detail. So things can be rasterized or ray traced, and they'll still show up. It's just that we're not yet path tracing them. And hair and single layer water are interesting because as material types and sort of custom object types, they go through their own sort of custom rendering paths. So at the moment, it doesn't make sense to path trace them, although we'll see how that goes. As I mentioned, we have compatibility with volumetric fog, but it's neither ray traced nor path traced. It's still being rasterized, but it has compatibility with this form of rendering. And likewise for post-process effects, your depth of field, bloom, motion blur, those are all still rasterized. All these things, theoretically could be path traced. They just get, without some improvements, they get expensive to do. So we'll see what the future brings. The NVRTX branch, like I said, it's a branch for optimized path tracing and ray tracing features. There's a bunch of stuff in it that will, like I said, there's nothing about the branch that or real-time path tracing that is tied specifically to RTX hardware. It runs everywhere ray tracing runs. But we do have a feature in the branch called SER, Shader Execution Reordering, that gives you faster ray tracing and path tracing on RTX hardware, specifically 40 series. And then we have one of our denoisers, NRD, is available in the branch. Like I said, the foliage feature for large-scale WPO support and efficient rendering of foliage meshes is also in the branch. Path trace decals, we just started doing that. That's also a feature there. And opacity micromaps, also recently added. This is a feature that, traditionally, if you do like a ray traced forest, all of the masked opacity areas on, tree fronds and so forth are going to be expensive to render. OMMs seek to solve that by eliminating the tests that go on with all that alpha mask work. DLSS, of course, is it's available as a plugin, but it's also part of the NVRTX branch, so you don't have to download it separately. It's pre-integrated, and it's DLSS 3.7, especially today. It's not just one technology. There's a lot of different technologies that go into this package. The one I want to highlight is ray reconstruction. All of the scenes I've been showing here have been built with ray reconstruction in mind, because as you get into real-time path tracing,
you're going to need
you want basically a more advanced denoiser, and ray reconstruction is the best we have right now. You can see in this video how ray reconstruction gives you sharper
Cyberpunk,
details,
baby,
sharper reflections, and it's generally better upscaling as you do more advanced ray tracing and path tracing type work. ray reconstruction will typically give you your best look. So we do a monthly web show called Level Up with NVIDIA. It tends to be very game focused. We talk about the technology we're working on. It's very informal.
This is the one that I was talking about. I don't have to give you the link. Just go to that QR code.
Almost always in the context of Unreal 5. Sometimes other, maybe SDKs or things like that, but it's pretty much all Unreal 5 these days. And that QR code there is a shortcut to some previous episodes. So if you wanted to check that out,
yeah, make sure you check the one
coming out on the 10th.
Okay, so that's pretty much it for the presentation. Obviously, this is something that I'm pretty excited about, and it's kind of weird because I was talking about this on my live stream on YouTube. We're in a point in time right now where the gamers are actually starting to split up, right? And what I mean by that is we have gamers who care about graphics like me, but you also have a lot of gamers, and growing, by the way, that would prefer playing low extra graphics just to get 999 FPS. And it's true. I've seen videos of people saying something like, I can't play unless it's 999 FPS. So it's curious to me, like, in a way, right now we're kind of going forward and going backwards at the same time. And I'm really curious, in 5 to 10 years, would we still, or would future players, obviously, would they still care about graphics, or would really just care about performance? Would they take over, is what I'm saying. Because honestly, if you watch, like, I see a lot of videos on Twitter or X of people playing like off the grid, it's Unreal Engine 5, playing on extra low graphics, just to squeeze some FPS back. So I'm pretty curious about the future of gaming, obviously. I hope that people will grow up and not just put everything on extra low and just go backwards in time just for the sake of performance, because they think, they're going to play better. But yeah, this is exciting stuff. You can already see this technology in games right now. Cyberpunk 2077, Alan Wake 2, those are the two that comes into mind that are really using this technology. And it's funny, when I covered RTX Ti, I think 2.5 years ago, I already said this is going to be great for horror movies or horror games and cyberpunk games, because it's crazy, man. Unlimited lights, shadow casting. Although, like you said, it's not going to work well with hair yet and whatever, so you probably didn't see a lot of human examples in here, but I'm sure eventually that will get better. But yeah, that's pretty much it for this video, man. Pretty excited about this. It's already here. I've made a video about a lot of this. We did do a live stream, like I said, in the QR code. I did do the Matrix demo with RTX DLSS 3.7, so go check that out. But yeah, let me know in the comments below what y'all think, man. And like always, I'll see y'all in the next one. Peace out.